We can start.
Yes. You can start.
Yes. So we're going to present our project, which is a comparative analysis of different energy systems based on financial and technical data in Akkar, Lebanon. So we're going to have a quick introduction, problem statement. We're going to do the methodology and present the results, and finally present the conclusion. So the global growth in population and the increasing demand of building services and comfort level, in addition to the rise in the time spent inside building, has led to increased energy consumption in the building sector. And this energy consumption is even increasing to reach high values, even more than the transportation and the industrial sectors. Next slide, please. So Lebanon is no different. It is experiencing increased energy consumption, especially in the residential sector, where the residential sector consumptions estimates to be ranging from 29 to 60% of the total electricity consumption in Lebanon. And if you want to look at the sources of electricity in Lebanon, there is the Electricité de Liban company, which generates electricity based on utilizing fossil fuels in power plants. However, some factors has led to electricity shortages in Lebanon. So people are using or are making use of the diesel generators in order to meet their energy demands. And of course, the diesel generators has a lot of disadvantages. So the increased energy consumption, along with the great dependence on the private diesel generators in Lebanon, is having a bad environmental impact, which is presented by release of greenhouse gases, including CO2. So there is a big problem which needed to be solved, and there are a lot of efforts that are being done. So ensuring a reliable energy and energy supply while minimizing the environmental impacts is an essential step. And when we think of sustainable, sorry. Okay.
Yes.
So when we think of, yeah.
Okay.
When we think of sustainable production of energy, we think of renewable energy, and it has different forms. So we have the solar energy, which is about converting sunlight into electricity. There's the wind energy that transforms the kinetic energy of the wind to the electrical energy. We have the geothermal energy, which generates electricity by harnessing the heat from within the ground. And we have the hydropower, which transforms the kinetic energy of flowing water into electricity. So if we move into context of Lebanon, we see that solar energy is one of the most attractive renewable energy sources, as Lebanon is specialized by its Mediterranean climate. It receives around 300 sunny days, solar radiations over 300 days. So we have 300 sunny days per year. So even in winter, we have solar radiation, and we can make use of it to generate electricity. Also, regarding the wind energy, it is favorable in Lebanon, as high speeds can be reached in which can be up to 7 meters per second.
Okay, going now to the problem statement. After a quick introduction about renewable energy and the need of energy in Lebanon, and especially in Akkar, we need to focus on a small information that the wind speed 7 meters per second is reached in Akkar, especially in Lebanon. So our problem statement now is about studying a small project. It's a house actually in Akkar. It's a real project taken from the market, from a company. It's a villa located in Akkar. We will be studying 3 scenarios to implement renewable energy solution to feed this house by electricity. First choice is to implement just on-grid solar system with generator, and just the solar panels with an on-grid inverter, and off-grid standalone solar system without a generator is based on solar panels and batteries, lithium batteries. An off-grid system with batteries for sure, plus a wind turbine, because this project is located in Akkar, and as I mentioned before, the velocity in Akkar is around 7 meters per second. And we will see the wind velocity data in PVSys in the coming slides. So going to the methodology. First of all, we calculated the day load, night load, and the total load of this apartment or this villa. Doctor, can I share my Excel also related to the calculations?
Yes,
because I want to
sure.
explain something related to them.
Yes,
It's hard
sure.
to put the Excel actually in the PowerPoint, but okay. Can you see the screen now?
Not yet.
No.
Yes,
What
now we
about
can.
now?
Yes.
Okay.
Yes.
So, okay, concerning the load calculation, actually we know the client, so we went to a site visit. It was actually during my work in this company, not now, but I know the client, so I asked him several questions related to his consumption. So we took the rated current for each appliance, and we took the usual calculation procedure, the time of use, and we then divided the time of use to day and night, and we divided also his load to normal load, the load that he uses usually, and something called additional load, which is not in the normal situation he uses this load, but he said that please design this project based on all the load. I wanted to cover everything, so that's what we did. And okay, here we can see that we divided the load to light day to see how much the solar panels can and the wind can provide us, and the night load in order to size the batteries or even rely on a generator in the case of on-grid system. So I will get back now to the PowerPoint. Hello?
Yes.
Okay, so now after calculating the day load and then the total load, we went to the simulation tools. Actually, we did some Excel calculation, as I can share them again, just to validate our results through PVSys, because we know that PVSys is the smart simulation tool, and it's used a lot in, especially in the Lebanese market. They use a lot the PVSys tool, but most of the data on PVSys tool are from 1990 and especially related to weather. So we need a factor of safety related to the numbers in the system and this simulation tool. So we used a validation tool on Excel. I will reshare it again. Okay. As we can see here, we calculated an estimated number of the panels using the rule of thumb, and the numbers were very close with a percentage of error around 2.5%. So, and all other simulation tools related to wind were calculated based on BEDS model, which is the best model to estimate the wind energy, and it was also calculated on Excel. So everything is shared in the report, and the Excel were shared with the professor also. So now moving to the results, and okay, the results. For the on-grid system, we can see that through PVSys, we reached a number of panels 40, the yearly production. And here's something to take into consideration related to the load. From the Excel sheet and from our analysis to the load of the house, we can see that most of the load is in the night time, not in the time of solar or solar light hours. So accordingly, using an on-grid system will not be very helpful because okay, this system can now produce, but what about tonight? And this system can now produce a huge amount, but it will not be fed to the load because there is no load actually at this time. And we can see this analysis here from the annual grid injection. We know in Lebanon, we don't have a stable grid to inject electricity in. So actually the grid is some generator or generator or a sub-generator network. يعني it's اشتراك actually, but we can't do this injection and benefit from it. So we can assume that they are useless amount of energy or loss of energy. And we can see that the annual production from the grid still with the solar panels, especially in the night time, the user still use around 15,000 kilowatt hour in an annual base from the grid. So it's not our best choice. And we did the same analysis for both the off-grid with batteries and the off-grid with batteries and wind to benefit from the wasted electricity during the day periods and store them inside batteries.
Yes, so the results of the off-grid standalone system, which is consisting of PV panels and batteries, as Amr mentioned, are in this slide. So we needed 40 PV panels according to PVsys, and we needed also 4 batteries. The yearly production is around 27,100 kilowatt hour, which almost matches the user needs, and this shows that the batteries were beneficial as they stored the energy, the excess energy in the day, and they are releasing them in the night. Also, as a comparison with the previous system, we can see that the yearly production or the amount of energy used in this system is around 27,000, which is greater than that in the previous system that is just 11,000. So we don't have waste of energy in this case. So in the previous slide, the off-grid system was able to meet the whole energy demand of the user without the need to get any energy from the grid. And this is shown by the annual production from the grid, which is 0. Now moving to the next system, which is the off-grid solar PV panels and wind turbines. This system, by just adding one wind turbine with a 5-meter diameter, we were able to decrease the size of the solar system by 8 panels and the size of the storage system by 2 batteries. And we can see from this slide that the energy production from the wind is around 14,000 kilowatt hours, and from the solar system it's about 13,000 kilowatt hours. And if we add them up, they almost matches the energy used by the system. So again, there is not any waste. So there's a point that I want to mention regarding the CO2 emissions. In this system, we were able to completely, as the previous system, so comparing the off-grid systems with the on-grid system, we were able to replace the generator. So here we have a generator which was running in order to generate the electricity to match the demand. But in the next 2 systems, the off-grid with the batteries and the off-grid with wind turbines and batteries, there is no generator, so there is more saved. The amount of saved CO2 emissions was increasing. Actually it doubled up to reach 12,000 ton of CO2 per year. So the advantage of this system is that it reduces the size of the photovoltaic system while still being able to meet the energy demand. And the advantage of the previous system, which is the solar panels and the batteries, is the increased saving of CO2 compared to the off-grid system, and the increased energy used from the system. So we don't have any energy waste, any energy which is being produced but not used.
Okay, moving now to the financial results. Actually, we shared the technical results, and it's important to share that by using the wind turbines, we can reduce the number of panels to 32 from 40, and also the number of batteries in the off-grid system. As we can see here, we used around 4 batteries, lithium batteries, 10.2 kilowatt hour, and when combining with wind turbines, we reduce this number, and we know that the most expensive part of the system, any off-grid system, is the battery. So this affected also the financial results. Actually, here we can see that we did a financial study from different parameters, and it's important to share that those parameters, all of them, were calculated through PVsys. And we didn't calculate it manually, actually, because it's more easier to take. It's more easy to take them from PVsys, and it will be more accurate. Also, we can see that the estimated lifetime for panels is 24 and 25 years. Sorry, and the lithium battery is 10 years. Concerning the wind turbine, there are studies that estimate the number or the lifetime for 30 and 40 years, but because it's not a very big wind turbine, the number of guaranteed years are around 25. And for the capital cost, for sure, this cost is also calculated through PVsys, and I will share now the calculation. It seems that the most expensive system is the combination of wind and off-grid. And for other parameters concerning the IRR, the ROI, the net present value, and the payback period, they are all shared in this slide. And it's important to take those results into consideration and combine them with the technical results to form this matrix of decision. And here we can see that first I will share part of like a sample from the PVsys simulation. Can you see the screen?
Not yet.
Yes.
Oh,
You
yeah.
can see it now?
Yes, now, yes.
Yes, actually, here all annual production and values and the tables are got from here, and this represents the diagram of losses. We can see here numbers concerning the financial. That's the single line diagram, and concerning all cost here related to equipment, we took them actually from a company. Official quotation from a company related to those prices. For sure, they differs. For example, the price of PV panels 1 month ago, before the VAT exemption thing, it was around 180 and 150. Now it's around 120. Those prices change, and that's everything related to the calculation of the financial parameters, the electricity, the ROI, the IRR, and this represents the net cash flow. And it's there is an important factor here that you can ask now, what about the wind payback period and the things related to the financial results of the combined system with wind? Okay, we calculated the BETS model alone in Excel sheet and then combine it with the PVsys. How can we calculate the values? Actually, there is a tool inside PVsys to add an external source in order because there is shortage sometime inside the PVsys. We can't like compensate the load and the demand. So we can add an external source. Usually it's a generator, but in our case, we added the wind turbines. There is no wind turbine inside the PV system, but we entered data related to wind turbines. For example, the lifetime, the production per year, and some characteristics in order to calculate the financial data related to the wind turbines. Because for sure, we can't take just from PV data related to solar and say that they are for both. And moving now to the matrix of decision. Okay, you can see the PowerPoint right now. Yes, you can see it.
Yes.
Yes, we can see it.
Okay. Okay, actually, the matrix of decision, it's not based on the usual market, because we did an exercise. We asked the client on the most important factor, and he said something very important. He said that he has something related to cancer in the gene of his family. So the most important factor in his situation is the CO2 emissions. It's actually for the first time we can see such a project, but for sure we can't weight things depending on literature while the client see other approaches. So we give the most weight or the highest weight for the CO2 emissions in our case. Secondly, he's interested about the cost, the annual production, the lifetime, and the maintenance and the noise. For sure, we didn't ask him the questions directly. We explained the things, and we said what's the most important. It depends. We shared everything in the report, and some interpolation were used to calculate.
Guys, please mute your microphones, please. Guys, mute your microphones, please.
Okay, we used interpolation to calculate values between 0 and 1. For sure, we gave 1 for the best performance and 0 for the worst one. And an interpolation were done. We could assume 0.5 for the medium approach, but we calculated the grade using the interpolation in order to see if it's more in the bad side or the best side. Yani, for example, comparing the annual production for the off-grid, it's 0.94, which is near 1. Yani it reflects a best performance. If we just put 0.5, this will affect the results. It's true in the literature, it's presented in literature, but it doesn't reflect the actual matrix of decision that will help us to take our decision on the selection of the project, the best project. And we gave also the capital cost. We divided the cost on 4 parameters: payback period, ROI, and net present value. Okay.
Yes, so this table shows the results of the decision matrix, where the grade for each system was calculated by multiplying the grade or by multiplying the grade with the weight of the grade, and then adding them all together. So it shows this slide shows that the on-grid system received the lowest grade with a grade of 0.35. Then comes the off-grid system with wind, which has a grade of 0.25, and finally the off-grid with batteries received the highest grade. And this result was expected, as Omar mentioned. We after asking the client, a big emphasis was put on the CO2 emissions, and the best two systems in this regard, which increased the amount of CO2 which is being saved, are the off-grid systems. So as a conclusion, the off-grid system was chosen to be the most reliable option, with keeping in mind that wind system integrated with off-grid system with batteries is also a possible solution.
Okay, before ending, it's important to mention here also that we still consider the off-grid system with wind an option, because as we can see in the matrix of decision, starting from lifetime, maintenance, and noise, the medium performance was taken 0.5 because they are actually qualitative factors and not related to quantity. So in some situation, we can change this weight here. For example, it could be 0.7, and this will affect the off-grid with wind. It will increase its grade. So we can still consider the off-grid and the off-grid with wind, and we can ask the client about the best choice for him at the end. So thank you. We're done.
Thank you.
Thank you, Omar, for the presentation, and Hilda. It's a good work, but just if you could have done the description of your systems, a little bit more about the processes taking place, it would be better. At the beginning, you did very well the financial analysis, the decision matrix, etc. But the solutions, the 3 solutions that you are proposing, should elaborate more on them. At least put figures on the systems that you are suggesting. If you are considering, let's say, all inputs, it's better to present all inputs you used in your presentations, the schedule, let's say the lighting schedule, the occupation schedule, because you need all of this to be able to assess the total load that you have.
In the presentation, Doctor, you mean?
At least you can describe briefly, yes, in the presentation. I know.
I'll tell you something about the load. We tried to take a screenshot and put it, but it's always half the picture. We can't put all the Excel. We tried to zoom out, but we thought that the best choice is, or solution is, to share both Excel and presentation at the same time during the presentation.
It's fine. It's fine. It's not a problem. But for example, for the systems, if you can just can you now describe a little bit the 3 systems you use? Do you have pictures showing the system implemented?
The system implemented.
The main components of your systems.
Okay. Actually, they are shared in. I will show you in the PV system, because we selected those parameters. The components are actually. Where is the financial? Okay, I will share something from here. They are all in the PV system simulation. Okay, we have the PV modules. We selected the Jinko, the 545 watt per peak, and we have the support.
So for example, here, do you have other options? Why you selected this item?
Why did I select this one, this Jinko? Okay, first, because it's the best. LONGi and Jinko are both the best brands for solar panels and the most efficient ones. And there is some limitation inside the PV trial version or student version in general. They don't include the newest brands. So we used the best one related to efficiency as we know in the market. And concerning the inverter also, for the on-grid, I selected this one, the Sun 2000s, which is Huawei. It's the most common inverter used for on-grid systems. And for the off-grid system, we selected...
Hilda, please. Okay, Omar. Hilda, can you continue, please?
Yes, so we selected those that are mostly used in the market and that are included in the PV system. And we've done also the optimization of the tilt angle. It is also included in the report. So to optimize the performance of the system to reach generate the highest electricity possible during the time of implementation.
The optimization, you mean you did several simulations, or
no?
Can you elaborate more, please?
Yes, Omar, please, can you share the report? I'm on my phone. I can't.
Yes, it's here. Yes, there is a tool, and I will share also the picture from the report with you, Hilda.
Yes, yes.
Okay. And we can also share, if you want, the simulation from the PV and try to do it from PV system. It's not a big deal. Okay, you can see now, Hilda, the picture.
Could you please make it bigger?
Okay, now.
Yes, so this tilt angle that is chosen corresponds to the optimum loss, which is 0%. We usually have the tilt angle to be equal to the altitude. It is agreed in literature to be equal to the altitude of the location, but we change it in our case to have zero loss.
And it's also important to mention that it's mentioned in the literature by Sassine et al. That the most or the perfect or the lowest losses in irradiation will be when taking the plane tilt 30 degree. It's mentioned also in the report. Both are presented in the literature, but we choose this because it showed us the lowest loss from irradiation, and on yearly basis.
Okay. Concerning the wind energy implementation, can you give more details about the formula you used?
Okay.
You used the maximum possible wind power considering the belt's limit, or what
Yes, no,
factors you consider?
for sure. Yes, I will share the Excel related to BETS model here. Just a moment. Excel. Okay. So as we mentioned earlier, we did some validation on our
Okay,
PV
please,
PV system
Hilda,
here.
can Hilda comment,
Okay.
please, Omar?
Yes, Hilda.
Yes, sure. So regarding the BETS model calculation, we calculated the output which could be gotten from the wind. And then we didn't take this, since this is an ideal output, we took into consideration the efficiency of the generator inside the wind turbine. So as Omar, you can go to the presentation. We have
Yes.
multiplied the power output with the efficiency of the generator to get a reasonable amount of wind energy.
I think BETS model, yes, here. We
Yes.
calculated the P real from wind.
So the P real is the ideal one, but then we took into consideration the efficiency of the generator.
Okay. And concerning the implementation with PVSys, can you talk more about the integration of your model in PVSys?
Yes. So regarding the PVSys integration of wind, we did the load minus the load that could be provided by the wind, and then we input the load on hourly basis and on the PVSys. So after calculating the wind or the energy that could be gotten from the wind on during the day by taking 8 hours per day, and during the night by taking 16 hours per night, we did the load demand, or the demand minus the wind power, and then we input it into the PVSys on hourly basis. So the PVSys took care of the load which has to be provided by the PV panels, and the rest was done during by the help of BETS model.
Okay, great, thank you. Dear students, do you have any questions for Omar and Hilda? Okay, so as you can see from this project, we can see the different steps of the design process, and we build the decision matrix to come up with a final decision. Now, concerning the decision matrix, now I will do for you an example today to review, to do a revision for the exam. So we'll see that the percentages, Omar and Hilda use percentages by asking the client, and this is what we usually do. But whenever we consider a project on the macro scale, we don't only ask one person, and we'll ask several persons that are affected by the project, and then we can come up with some statistics in order to put weights. For this exam, we don't have to know how to put weights, because we'll learn this after. But just for your projects, you can implement the decision matrix as we mentioned before by calculating the score as we did. And now we'll do an example on this together in the revision session. Okay. So I will start a new session in order to do revision for the exam.
Okay.
Okay, thank you.